Hello, my name is Evgenii Zheltonozhskii, and I'll talk to you today about entropy encoding for neural network inference, and in particular, the convolutional neural network inference. And we'll start from motivation. Why is it interesting? Why is it interesting to do entropy encoding? I'll give some mathematical background for those who don't remember what's Huffman coding and PCAs. And then I'll talk about two of our papers. And we'll conclude with some conclusions and directions for future work. So first of all, who am I? I'm master student in Technion under supervision of Alex Bronstein. And you can see my contacts on the slide. And our group worked for a while about some custom hardware papers, quantization papers, and some papers about custom hardware design. And today I'll talk about two of those, which utilize similar idea in a bit different way. First one is feature map transform coding for energy efficiency and inference, published in IGCNN this year. The second one is CAT, compression aware training for bandwidth reduction, still unpublished, got good reviews from both ICLR and CML, but got rejected. So what is the motivation? We want to run neural networks on edge device, cell phones, Internet of Things, stuff like that. But it's very energy demanding. It requires much computations. How can we reduce all those requirements? And one of popular solutions is quantizations and pruning, other ways of compression. Both shows improvement over full precision networks. However, a large part of energy footprint of edge hardware is due to data movement to and from off-chip memory, RAM. And in those papers, we utilize transform domain quantization of the activations and lossless variable length coding, which I'll talk later. So some background about energy consumption in CNN inference. The topic was very popular, and already in 2017, Young noted that communication with external RAM amounts to large part of energy footprint. In their case, it's 70%, and there are other papers that show similar numbers. Moreover, some papers like TPU paper by Google and others noted that not only power consumption, but also computational speed of accelerators is often memory bounded. And people are fighting this with different approaches. For example, amount of caches grows really fast nowadays in CNN accelerators. People are pushing hundreds of megabytes of cache to get faster communications with the memory. And communication can be obviously reduced if we require less bits per input per rate of activation. And 16-bit, as you probably all know, is definitely almost a standard now for both training and inference. 8-bit can be often achieved without short inaccuracy and without some complicated tricks. If we try some more involved methods, we can get down to 2 up to 4 bits without small impact in accuracy, at least for ResNets and for image classification. If you use, say, MobileNet or EfficientNet, probably will be harder to quantize those. If you do regression, it probably will be harder to quantize those too. But still, all those methods are involved. They often require training networks from scratch and require some complicated training protocol. And they usually hurt accuracy in some way. And what we want to do is to somehow reduce memory bandwidth without hurting accuracy at all, or hurting accuracy as low as possible, which means not changing the representation of weights and activations. And there is existing line of works. First of all, Han already in 2016 used Huffman coding, which I'll talk about later, to compress network weights. And Vijayata used deflate, which is more complicated algorithm to improve compression rates. Chandra also tried to use Huffman coding to compress feature maps. And two more recent works which we'll compare to is Gudovsky et al. And Kavigela and Benini. And they tried some different approach to compressions, such as run length encoding algorithm, which utilize sparseness activations. Okay. So let's start from some background. I'll try to explain mathematical things which we'll utilizing, and probably some of you are familiar with those, and you can skip this part. So what is entropy? Entropy is the theoretical rate of how good can we compress some signal drawn from non-random distribution, and it equals negative binary logarithm of the random variable. And this rate assumes that each symbol is compressed by individually, and that they're drawn from some independent distribution. So obviously you can improve if you know something about connection between symbols, or if you encode more than one symbol at once, such as run length encoding. And there are different entropy encoders that utilizes this approach with encoding each symbol one symbol at a time using known distribution. And one example of those is Huffman coding. The basic idea of Huffman coding is just to give shorter codes to more frequent symbols. And let me show you an example. So we have 4 different symbols, and the default approach is just to give 2 bits to each of them, 0, 0, 0, 1, 1, 0, and 1, 1, which would obviously take average 2 bits per symbol. But if we know the distribution, and we know that A1 and A2 are much more frequent than A3 and A4, we can do better. So we start from A1, which takes only one bit per symbol, and we pay for that by giving A3 and 4 3 bits per symbol. And if you calculate expectation of amount of bits per symbol, you'll arrive to a number which is less than 2, which means we compress the signal just by using those statistics. And the advantage of Huffman coding that it's very simple. It just requires building this tree, and then you can just map each symbol to its code. And the decoding is also very simple. The disadvantages is that it's bounded by one bit per symbol. So you can get, if the entropy is very low, less than 1 bit, you can benefit it. And obviously this reduces the effectiveness of the method. Another thing we'll need is principal component analysis, or PCA. PCA is a linear transformation which makes different components of the vector uncorrelated. And if you're talking about information, that means that there is no overlap of information between different components of the vector. And obviously, since we don't need to store the same information twice now, this reduces the total entropy of the signal. And now I can start from our first paper, feature map transform coding for energy efficiency and inference. And the idea was to utilize those things in post-training regime. So we don't need to train network from scratch. We take the trained network and reduce its memory requirements. And first of all, decorrelation of the signal not only improves its entropy, but it also improves the quantization error. So if you take correlated signal, you can see that there are many empty bins, and there are many bins which are not populated, and the bins themselves are relatively large. But if we decorrelated the signal, the size of bins reduces, which means we reduce average quantization error. And there are also no empty bins, which means there are higher population of each of the bins, which allows us to utilize them better. And Another thing we can do is to give components with more information. In our case, this is horizontal component. We can give them more bins while giving components with less information, less bits, and in this way improve quantization error even further. And this, together with the idea of the reducing entropy, takes us to the main idea of this paper. And you can see in the scheme, so we take the output of the convolution, we apply batch normalization if there is one, and then we apply the principal component analysis along channel direction. So we take one pixel, take all the values of this pixel on different channels, and we apply PCA on these values. Then we quantize the output, perform variable length coding, in this case Huffman. We used Huffman coding, and only then the data are written to the memory. And we perform the same chain backward when we read the data. We decode the Huffman coding, apply inverse quantization, inverse PCA coding, activation, and pass it to the next convolution. Since PCA applied along channel direction, we can regard it as a convolution, one-by-one convolution. And one thing we can do to reduce the computational overhead is to fold it together in this batch norm in the convolution, which means we only need to calculate inverse PCA and Huffman coding as compared to usual inference. And there are some exceptions to this approach. For example, if we have grouped convolution, then PCA, which is ungrouped convolution, cannot be folded into convolution, especially in depth-wise case, where we can say just let's do a PCA over a smaller amount of channel. But since usually depth-wise convolution is followed by a regular convolution, what we can do is to move activations before the PCA transform and fold the inverse PCA into the following convolution, which still leaves us only with single one-by-one convolution for overhead. And in case of one-by-one convolutions, overhead becomes larger because we need to do 2 convolutions instead of 1 per layer now. But in case of regular 3x3 convolutions, the overhead is more or less negligible. It's around 10% of computations. And let me show you the results. We used 8 and 4-bit weights and different size of activations to achieve rate distortion curves. Rate is measured by a bit per value and distortion by accuracy. So the dashed lines are theoretical entropy, so just entropy of the signal, while the solid lines are real amount of bits we need to write with Huffman coding. And as you can see, we can, at least in case of resonance, we can reduce entropy with losing only 0.5% or 1% the weights. We can achieve significant improvements in compression of written activations. Obviously, in case of mobile net, which is much harder to compress, we get less benefit, but we still can improve rate at least a bit. And we perform various ablation studies. I won't talk about all of them, but I do want to talk about this one, which studies how each part of the approach affects the compression rate, bits per value. So the baseline accuracy is shown in dashed line, in black dashed line, and we show that both variable length coding and quantization and PCA are important parts of the approach, but important part is that there is a synergy between PCA and variable length coding. So, for example, improvement of PCA as compared to bare quantization is less than improvement of PCA if we use VLC. So red line compared to cyan gives less improvements than blue one compared to green one. And similarly, the blue one compared to red one is less than green compared to cyan. So adding VLC benefits more by adding PCA. So, and as you can see, right, if you compare to a full precision to quantized baseline, can achieve twofold compression without losing any accuracy. And we also take a look if we can truncate PCA, since the later components of PCA contain very low amount of information. The one thing you can do is just drop them at all and forget about them. And if you allow, this also will reduce the computational complexity, because inverse PCA and forward PCA are now smaller matrices. You need less, so it's the convolution with less output channel. And as you can see, we can benefit from dropping those components from computational wise, but we'll obviously lose some bandwidth. And it seems that you can drop too much components, even 75% produce a significant drop in compression. We also, to check the energy rate or how many variants stored in those PCA components, we studied it for different networks, and you can see the more compact networks like MobileNet get more compressible activation. So 30% of eigenvalue already stores most of the energy, which might be a bit counterintuitive. And finally, we played with different PCA shapes. So as I told earlier, we used PCA in channel direction. So this would be 1 by channel orange line. And this is obviously beneficial from computational point of view, but we wanted to check whether it's good from a compression point too. And we calculated a bits per value, accuracy is a function of bits per value for all those approach without taking into account computational complexity. And we tried both larger kernels, maybe 2 by 2 or 4 by 4, and less channels, so fourths and half of the channels. And as you can see, actually 1 by channel block is one of the most optimal. The only one that outperforms it is 2 by channel and low compression rates, but obviously that would increase the computational complexity too much, so we didn't take this approach in our paper. We stick to 1 by channel. And we also try to implement some baseline in hardware to check whether we get the benefits, and you can check the paper and see that it improves in FPGA case the utilization and power consumption. And the next idea was whether we can do better. How can we do better with this compression? And the answer is to be aware of what you want to do in the training. So if you want to reduce the entropy of the activations, you can add some penalty during the training and improve the entropy of the activations. So in this case, you can also reduce the memory bandwidth even further. The problem is the entropy as defined is not a differentiable function, especially since we're talking about quantized signal. This might be a bit problematic. So you need somehow to redefine entropy. And we redefine entropy in a differentiable way, or approximate entropy in a differentiable way. And we use the usual trick. If you remember, the entropy definition is minus sum of p times log p. And in our case, the probability is a amount of X is quantized to this particular value. So we talk about quantization. If we take 8 bits for each bit, for each of 256 values, we check how often it appears. And how we decide to which value we quantize the floating point value. This is, we take the closest bin, the closest quantized value, and this is argmin of distances between X and Q. And at the moment you see argmin, if you work with neural networks, you need to say, aha, we can replace this with softmax. So we replace argmax with softmax and we acquire differentiable approximations. So now when we have the differentiable approximation, we can use it as a part of our loss function. And adding it as a regularization to loss function allows us to reduce the entropy. And so in the left, you can see the distribution as a function of time with entropy regularization, and we start from pre-trained network and fine-tune it with this regularization. And as you can see, in first epoch, we got some normal distribution with maybe standard deviation of 1.5 or maybe 1. And it becomes much denser, and you have many zero values, and bins near zero becomes much more populated. So those two bins alone take already 60% of the populations, which obviously say us that the entropy of this distribution should be much smaller. And as you can see, the stronger the regularization, obviously, the better the results. So especially for, you can see it from the zero bin, it grows very fast with the regularization. It's almost twice as high with strong regularization as compared to no regularization at all. And now we applied those methods we talked about. Now we don't need PCA because we explicitly reduce the entropy of the signal instead of reducing it implicitly with PCA. So we drop the PCA. We have no computational overhead now, but we paid for it with the training. And here we compare with methods I talked about in the beginning, EBPC by Cavighelli and GF by Gudowski. And as you can see, we achieved better compression for negligible drop in accuracy, or even better accuracy and better compression. And in this paper, we also tried different networks, not only RiseNets and MobileNet, but also we worked on SSD, which is a regression task for image for object detection. And also, if we push it towards very complex representations, if we put very strong regularization, we actually become bounded very strongly by Huffman coding. As we talked earlier, Huffman coding can overcome 1 bit per value, and for ResNet 18, we managed to get less than 1 bit per value entropy in some cases. In MobileNet, where compression is not that strong, the overhead of Huffman coding is less, but for 8-bit it's still noticeable, 50% maybe. And we also worked on BERT. So, and we tried to compress both weights and activation in this case. We applied BERT on sentiment analysis task on Cola dataset. And in this table, you can see comparison with quantization to 8-bit with and without regularization. And the improvement is almost twofold. For both weights and activations of embeddings, and a bit worse for activations of fully connected part of the BERT. But once again, the drop of the metrics is almost negligible. So let me conclude. So we've shown a proof of concept of energy optimization in neural network inference hardware by compression activations and possibly weights. In post-training regime, we can reduce by 60% relatively to 8-bit baseline, and this gives us less than 2% accuracy degradation in ResNet. If we add regularization during training, we can reduce bandwidth by 70%, no computation overhead, all this relative to 5-bit baseline for image classification, and we can apply it also to object detection and to NLP, BERT. The computation overhead is very small. I haven't talked about computation overhead of Huffman coding, but even not in custom hardware, it is negligible, less than 5% of runtime. As for directions for future work, first of all, the main problem of this approach is that you need to intervene between writing to memory and computation, which can be done on commodity hardware. You need custom hardware for it, ASICs or FPGAs. But this is very simple improvement and can be used even if you don't apply neither of approaches. You don't use neither PCA nor a regularization during training. You still can get some benefits, not that strong as if you do the training. And that's it. I'll be happy to answer questions during our live session, and or if you want to connect me in any way, you have seen my contacts in the one of the first slides. Thank you for listening, and goodbye.